So good morning, everybody. Thanks for coming. We have again a colloquium, Saber Ochoa colloquium, that today is going to be given by Dr. Sergio Martín, who made his PhD at the ARAM in Granada, the Instituto de Radioastronomía Milimétrica. Then he carried out several fellowships at different observatories, like the Submillimeter Array, run by the Harvard-Smithsonian Center for Astrophysics in the United States, or NOIMA in France, and ALMA in France as well, and ALMA in Chile. In fact, now, today, he's currently working at ALMA as interim project manager, so in the top of the responsibilities for delivering the science programs in ALMA. He's got more than 100 papers with more than 4,500 citations. He has been invited more than 10 times to international meetings, and he has been serving for time allocation committees and human resources selection committees in quite a number of times, and he's got quite a strong record for software development, as you will see today. He's particularly interested in the study of molecular material in the nuclei of galaxies, and his research studies have mainly been focused in the description of the chemical complexity of the interstellar medium within the central few hundred parsecs of nearby starburst galaxies. He also tries to get insights on how the chemistry is affected by the extreme phenomena and conditions taking place in these central regions. And in this talk, he will talk about molecular spectroscopy at a resolution for everyone. And you will see that we'll be combining all his capacities in the deal of an analysis of data and also software developing. So thank you very much, Sergio.
Thank you. Thanks a lot for inviting me to come over. I mean, since I was coming from the ALMA several years after ALMA conference in Italy, it was an excellent opportunity to pass by. And unfortunately, I could only stay for 2-3 days. So I have to fly tonight to Santiago. Hopefully, I will be able to take my flight given the political situation. But if I cannot, then maybe I will come back to Granada and stay a few days more, right? So thank you for hosting me here these days. So yes, so I wanted to talk to you about this very broad thing, which is called molecular spectroscopy at high resolution for everyone, right? And this is basically hiding the topic that I like, which is astrochemistry, right? And astrochemistry in particular in the center of galactic nuclei, right? When you hear about astrochemistry, probably you can be scared, and some of the talks that you will hear about astrochemistry will deal with these kind of things, right? This is a work that we carried out towards the galactic center. And the idea here was to study the abundances of molecules, nitrogen-bearing molecules, to understand how the chemistry of nitrogen proceeds within the molecular clouds in the galactic center. So this kind of talks is something like, astrochemistry needs you, right? I mean, we need people to understand the astrochemistry by itself. But what I will be talking about here, it's more like this. It's astrochemistry as a tool. The way I deal with astrochemistry is not, well, I have to understand astrochemistry by itself, but I try to use it as a tool to identify the different physical processes within galactic nuclei. And this field has been blooming in the recent years, in particular with ALMA, and will continue blooming with NOIMA, with NGVLA, and with SKA. I will just briefly mention SKA at the end of the meeting, and just to show you why this is that almost every millimeter, submillimeter, and centimetric facility has been improving the bandwidth of the receivers and their backends, right? And this is, for example, the observations of 12CO carbon monoxide in a galaxy from observations in 2005, 2007 with the IRAM 30 meter here in Granada, right? But then just a few years later, what you had is something like this, right? Even if you are targeting, again, the carbon monoxide line, if you integrate deep enough, you have all these kind of features here from which you can extract some information, right? You can basically measure the line intensity or integrated intensity or equally the column density or abundances of this molecule to understand what's going on this galaxy, right? So it's not that astrochemistry needs you, it's that you want to use astrochemistry and you know it, right? But you do not know how to do it. So what I will be talking here, as I said, is e-Astrochemistry. For me, this is extragalactic astrochemistry, okay? But these kind of tools can be and are applied to many other fields within the galaxy or in other galaxies, right? or in star-forming regions in protoplanetary disks. This is a quick look to the history of extragalactic chemistry. This is a plot that they made a few years ago, and this is the number of species detected through time, the cumulative number, and these are the same thing but isotopologues, right? So at the beginning of times in the prehistory, we had the first detections of OH and formaldehyde in the 70s, right? And actually, carbon monoxide came third in 1975. And this is the first detection of carbon monoxide in NGC 253. This was just a couple of years after the detection within the galaxy. So extragalactic is always catching up very quickly with what we do in the galaxy. What's impressive with the new receivers and new observatories is that this kind of the detection of carbon monoxide on NGC 253 is something that you can do in the 30-meter here within a fraction of a second with probably 10 times better signal to noise, right? So this thing has improved a lot. So it was actually with the advent of these big observatories like the CEST telescope in Chile and the IRAM 30-meter here, when we pass into the history, right? There's a series of papers in which there were more and more molecules detected, and basically they were doing it because they could do it, right? And then they were trying to understand the dense molecular gas in galaxies. But then there was the need of a new step, which was the carrying out of spectral scans. So it was not targeted observations, but then we were going broad, and then we spent a lot of time to do full spectral scans, which were giving us the full picture of the chemistry in galaxies, right? And this is the present. This is where finally we can do like blood samples of the molecular gas in the central regions of galaxies. I had another updated version of this, but basically now we are a bit stuck here, right? We are now in the 60s, more or less, of species in the extragalactic environment. But from one slide that you will see later, from a work that we are currently carrying out, we are already on the 100 of species. Okay. So basically, what are the main roles, main physical processes that we can find in the extragalactic ISM, right? Well, basically, when in the starburst environment, we probably have a lot of molecular gas fueling into the center of the galaxies, and this gas is compressing and colliding, and it's generating shocks. Then we have this gas, called, this compressed gas, is forming stars at a really extraordinary pace, and this newly formed massive stars is photodissociating the environment, and then this starburst is also producing shocks due to supernovae, right? And this is in the form of outflows, and this is also impacting the ISM. When we have at the center of the galaxies an AGN, this AGN will produce a lot of X-rays, a lot of radiation that will be affecting the surrounding material, and then also high-velocity shocks due to the black hole jet and outflow, right? So this is all these phenomena, all these physical processes will have an impact on the ISM, and it will have an impact on the chemistry that we observe on the ISM. And this is what we are trying to study, and this is what we are trying to study, how to use this footprint on the chemistry to understand the processes in the galaxies, right? So this is more or less an outline of the talk, which was not the first slide, but this is already the 15th or something like that. So at the beginning, I'm going to show you some of the work that we've been working on during the last decade, right? In which I will be like showing you how to use different tracers, like what tracer can be used for what, right? And I will put an example of a study that we just submitted to, it's under review, regarding the use of these traces to trace the star formation history in the galaxy. And I will show you this MatCuba software that we've been developing for more than a decade now with a group in the CAB in Madrid, and a large program that I'm currently leading at ALMA. And then I will show some other examples outside of the extragalactic, or well, outside of the nuclei of galaxies, which is basically the study of the chemistry around this black hole at the center of the galaxy, the molecular gas in isolated galaxies, which is in collaboration with Lourdes here in the IAA, and also regarding the environment around where the GRBs are produced. This is a collaboration with Antonio Dogarte here, and then also some prospects for high redshift and SKA. So here are some examples. So the talk is going to be just about this. It's just showing you tools. It's just showing how we are using these tools currently on the extragalactic ISM. So the first one is the SIO. SIO is kind of the molecule. It's the molecule that nobody doubts that it's a tracer of shocks. all the other molecules that I will show you here, well, you will have the chemist saying that, well, probably it can be produced like this, can be produced like that, but SiO is a refractory molecule which is contained in the dust grains, and it is only released into the gas phase when these dust grains are shocked and destroyed, right? So it's a good tracer of shocks. Here I showed you two maps of carbon monoxide. This is NGC253 at 1/2 resolution with the SMA. This is an image already almost 10 years old. We have even higher resolution data from ALMA now. But this is a nice comparative because what you have here is not an extragalactic object. This is the center of our galaxy with a small telescope. So right now we have a resolution similar to what we have with a small radio telescope towards our galaxy. So we can almost do a one-to-one comparison. But the SiO distribution from a map from the MOPRA telescope is something like this. And what we observe in the galaxy is that when you compare the abundance of SiO in quiescent clouds, and when you compare it with the clouds in the galactic center or in massive star-forming regions, there's a jump in the abundance of 4 or 5 orders of magnitude. It's enormous. So it's a very good tracer with a lot of dynamic range, right? And a similar thing we observe on galaxies, right? This is the galaxy M82. This is an evolved starburst, mostly dominated by photodissociation regions due to the already old star formation there. And this is a map from Santiago García Burillo, already almost 20 years ago, right? This is with Noema, with ALMA, actually Plateau de Bure at the time. And we see that within the disk we have a very low abundance, but there's a 1 order of magnitude of difference in this shell produced by supernova events, and the same in the outflow. We observe the outflow on SiO, right? So take home message, SiO shocks, easy. This is also an old example. We have many more examples now with ALMA, but since this was kind of the first prototypical example I still like to show, this is a work from David Meyer and Jean Turner. And this is showing how the same galaxy, in this case IC342, it's kind of a Milky Way type with a starburst at the center. This is how different it looks, a galaxy, when you look at different molecules. So somehow the molecules allow you to dissect the galaxy in the different processes. So in the top row, you see the CO, the C18O and HNC. Even though this is more tenuous material and this is dense material, it's basically tracing the whole galaxy. This is the spiral, kind of a spiral shape at the center of the galaxy. But then when you observe things like C2H or CS, C2H, for example, I'll talk about this later, it's formed out of the dissociation of PAHs, of polycyclic aromatic hydrocarbons. Right? So when you have UV radiation, you break the hydrocarbons and then you form C2H. And kind of similar thing with CS. It's also produced by UV, enhanced by UV photons. So when you observe these two molecules, you only see emission at the very center of the galaxy. And this is basically the central star cluster photodissociation, the nuclear region. But then other molecules like HNCO and methanol, it's completely opposite, right? There's almost anything at the center, and everything is here on these spiral arms. And this is basically, and I showed you here as a comparison also SiO, which looks very similar to HNCO and methanol. And what happens here is that we have the molecular gas which is flowing into the center of the galaxy, and this gas, we have the orbits, these X1 and X2 orbits, right, and in a bar potential, and then when the gas is falling, changing from the X1 to X2, when it's falling into the center, this gas is compressed, this gas is shocked, and this gas is releasing this material, this SiO from the dust grains, and similar thing with HNCO and methanol. These are also formed in the dust grains, and it's released into the media by these shocks. And actually, HNCO, so the three molecules are kind of tracers of molecules, but HNCO is particularly interesting. And this is something that we saw a few years ago, and it's because different from SiO, HNCO is also released from the grains, but as soon as you illuminate it with photons, with UV photons, it's absolutely disappearing. And then we have a really large range of more than an order of magnitude. This is a number of galaxies, right? Observing this here in the bottom, you have the abundance of HNCO, and here is the abundance of CS. Basically, it's the isotope 34 of CS. And what you see here is an enormous dynamic range between young starbursts, intermediate star formation starbursts which are already ending probably the starburst period, and starbursts which have already almost done, are almost ready done. And this line here is basically telling you the fuel exhaustion of gas. Basically, in this line, we are seeing how the gas is being depleted, how the gas is being consumed by the star formation. Here, it could be the enhancement of UV fields, but there was a paper that was kind of putting this into doubt. But this is absolutely clear. And actually, as I said before, MHE2 is a galaxy which is dominated by photodissociation. That means that almost all the fuel is already consumed, and then all that is left is mostly photodissociation. And this is observed in a number of molecules, which are basically ions which are produced in these photodissociation regions, right? So take-home message, HNCO, fuel, right? If you have a lot of HNCO, that means that you have a lot of gas, which is highly shielded, and it's actually this shielded gas which you use for forming stars. And then we have the eternal quest for molecular diagnosis of galactic nuclear activity. This is a very usual plot, these BPT diagrams that in extragalactic are used to differentiate between H2-dominated starburst galaxies and AGN, galaxies with an active galactic nuclei in the center. And then you can do the distinction here. This diagram is found in many other formats, in many other ratios, but it's basically like that. But what happens when this powering source, this potential AGN, is absolutely obscured by a lot of dust and a lot of gas, sometimes with more than 1,000 or 10,000 magnitudes of visual extinction, right? So basically, there's no way we can trace these AGNs with optical, infrared, X-ray, or whatever, right? They are quantum thick, so basically there's no X-ray signature. So, and the interest of finding all this obscure AGN is that the number of these obscure AGN will have a direct implication on the total number of AGN in the universe, and that has cosmological implications, right? So there were some other diagnostics proposed in the literature, like this work from Marcus Spoon, and in which we have here the PAH, as I said, the PA, this is polycyclic aromatic hydrocarbons, and basically its equivalent width is basically telling you the distinction between AGN and starburst, right? While the silicate strength, the strength of the silicate absorption in the infrared is telling you about the obscuration. So basically here you can still do the distinction, and he was dividing this in a number of boxes, but as you go up, oops, what did I do? As you go uphill here, then you start seeing things like ARP220 here, which is, and then things which are even more obscure. These galaxies here, I will not talk about them, but these galaxies are extremely obscure, and they are extremely compact. They have like 10 to the 11th solar luminosities within a few tenths of a parsec, which is something which is mind-blowing for the star formation community, right? So again, there are sources which are absolutely obscure. So how can we differentiate them? And then these are the number of diagnosis plot that was proposed on the literature, right? And this was based on the molecules HCN and HCO+ as a diagnostic. Why HCN and HCO+? Well, I mean, after CO, these are the brightest molecules, so people was trying to do something with what you can observe, right? And it was in all this story started in 2002 with the work of Kotaro Kono, in which he was basically plotting the abundance of HCN and the HCN over HCO+ ratio. And then he was seeing that, most AGNs were on this part of the diagram, right? Here you had kind of a mixture. Then similar work, but with using different transitions of HCN and HCO+ was done by Melanie Cripps. And in this work, we were seeing whether there were difference of excitation. And again, you had this kind of diagram where starbursts were somewhere here, AGNs kind of here, but not very clear. The work from, in this work with Francesco Costagliola, we were trying to put some other thing into place, so including the emission of HC3N, but it was not very clear. And there has been follow-up works, and for example, in this work from George Privon, he was using 58 local galaxies, and you could see that most starbursts lie on, when you observe this ratio, HCN, HCO+ ratio, most starbursts are on this kind of below 1, and then AGNs are kind of higher, but you have a huge dispersion. And similar with this work of Imanishi, Naka Imanishi is doing he has a lot of ALMA data, he's collecting a lot of observations. And again, the starbursts are kind of below 1, but then the AGNs is like, it's all over the place. So this diagnostic is not clear. And this is, once again, a similar diagram at high resolution. this diagnostic gets much better understood at higher resolution. And for many years, almost 20 years, in the mind of the community using this diagnostic, there was this idea that HCN was overproduced in X-ray dominated regions. So it was actually the radiation from the AGN which was enhancing the HCN. But now, with the resolution and sensitivity of ALMA, we can actually peer into these centers, and this is a couple of works that we did just a few years ago. And here we can see, when you observe this at high resolution, that this enhancement of HCN is not happening right at the AGN, but it's happening it's happening in the surroundings of the AGN, but the maximum is not at the AGN. So that means that it's not the AGN which is enhancing this kind of molecules. There's something else related to the AGN, but not the AGN itself. And actually, the chemical models show that, for example, in the formation of HCN, we have this reaction here that has a very high energy barrier, and it's only when this energy barrier is overpassed when you can overproduce this molecule. And this is basically happening. This is basically a high temperature chemistry which is going on, right? So probably there's something related with a high temperature chemistry which is not the AGN itself. And what's proposed is that actually this is related to the jet. This is related to the outflow, which is heavily impacting the ISM, and this high temperature chemistry, it's producing this enhancement. So then, HCN, HCO+, mechanical heating, that's what we think. It seems that it's working finally, but still in the mind of people, you still go to a specialized conference and people is still saying that, it's the X-rays which is enhancing this. This actually cannot be, because the sphere of influence of the AGN is really, really small, like a few tenths of a parsec, right? So there's something related to the outflow which is enhancing this. And actually this is actually observed, this is actually seen observational. Already 10 years ago, we could see that in Markarian 231, we have the HCN emission, and we have these wings, these high-velocity wings, which are not seen in HCO+. It's only on HCN, and this is tracing the outflow. The outflow is very, very clear on HCN. And we have another example here, very recent example from Loreto Barcos Muñoz, in which we have the molecule, the galaxy R220. R220 is a late state merger in which we have two nuclei separated by 1 arcsecond, and it's heavily obscured. So basically, the center is opaque almost at every wavelength. There's only a small range in between radio and millimeter of range where it's not optically thick. And in the literature, there has been always claims that there's an AGN on the western nuclear, right? And just recently, the signature of the outflow was detected with very deep ALMA observations. And actually, the interesting thing here is that this is the red-shifted and the blue-shifted sites of the outflow, right? Observed in HCN. But when you go to CO, it's not so obvious. So somehow it's way brighter on HCN than it is on CO. And once again, this is permeating the idea that the HCN is enhanced on the interaction between the outflow and the ISM. As I said, these regions and the central galaxies of obscure galaxies are extremely obscured. And the question is how we can peer into these obscure regions, because even continuum observations at 1 millimeter or 3 millimeter in the tail of the dust are extremely obscure and opaque, right? And one of the answers or the possibilities is vibrational excitation, right? In this case, we use the excitation, specific conditions of excitation to really peer into these regions. And this is the example of HCN. HCN is this beautiful 3 atoms molecules. Typically, we observe the rotational emission, but it has these vibrational levels, which are these V2 levels, which are the bending modes of HCN, and then we have the stretching modes. But the bending modes already have an upper level energy of 1,000 Kelvin, so it's very high energy, and these ones are actually not detected on the ISM. But how can we observe these things? I mean, it's very high excitation compared to the typical low temperatures that we find on the ISM. And the answer is that these cannot be excited. So these are the ground vibrational state, and this is the first vibrational state in this bending mode. And to overcome this difference, I mean, we cannot do it just by collisions with hydrogen. We would need densities of 10 to the 11th per cube centimeter. That's huge densities that we don't find in the ISM, at least not in many regions, right? So this means that this has to be radiatively excited. Basically, what we need to observe this molecule is something like this. Basically, we have something very hot in the center. It could be still an AGN or a hot starburst, and then we need a lot of material to create some kind of greenhouse effect, so that there's a lot of absorption of this radiation. And by this absorption of this internal heating, these molecules are vibrationally excited, and this is how we can peer into the center of these galaxies. This is once again the example of R220 and a work that I published 3 years ago, in which you see here the molecules of HCN and HCO+ are, when you observe at the center in both nuclei, is absolutely absorbed and self-absorbed, right? This thing here should be like a Gaussian like this, but it's absolutely absorbed. You see here this huge absorption towards the center. So these molecules do not peer into the center, but the vibrational emission is a perfectly Gaussian shape. When you do the mapping, it's really, really centered at the center of these two nuclei. So you are actually peering through this opaque dust. So vibrational emission overall, both in galaxies and within our galaxy, is showing internally very, very dense material. Okay, so all this blah, blah, blah is like, I'm showing you different tools, different molecules that serve you to trace something, but now we put these things to work. This is a very recent paper. Well, actually, yes, this is the work from Leroy. And what we are going to do is to make use of vibrational emission of HC3N and HNCO, that I told you HNCO is fuel, right? This is available fuel, right? So this is a work from Adam Leroy, and he was observing the emission at 1 millimeter of NGC 253. This is the galaxy that I showed before compared to the center of a galaxy, but now at a very, very superb resolution. Now we have a resolution of 2 parsecs in these maps, right? And then you see the individual condensations. You see the individual giant molecular clouds in most of cases forming superstar clusters. So the sizes of these clumps are something like 2-3 parsecs with 10 to the 5 solar masses, and then all the sources are associated with emission at 36 gigahertz. And assuming that this emission is coming from free emission from ultra compact H2 regions, in this work from Leroy, he was able to estimate that each of these one was emitting like 10 to the 8th solar luminosities. So the total, if you compare that with the total with the volumetric luminosity of NGC253, this clearly shows that there's a large fraction of luminosity which is hidden in an early phase. It's hidden in a proto-star phase. And this is what we try to observe with vibrational emission. So if you have the same map here, but now observe with the vibrational emission, here in contrast, you see this kind of small clumps of vibrational emission. We can kind of constrain the source sizes, first because they seem to be unresolved with a resolution of 0.1 arcseconds, and it has to be more like 12, on the order of 30 milliarcseconds under the assumption of optical thick emission of HC3N. And what we observe in each of these clumps, based on the luminosity, one of the good things of HC3N is with the vibration, you have, I didn't put the spectrum, but you have the main transition, and then you have the vibrational transitions. And with that, you can estimate the vibrational temperature, and this temperature you can equate it. You can assume that this is the internal heat temperature, and you can estimate the luminosity, and then you estimate that each of these clumps have a luminosity of around 10 to the 8th solar luminosity, which is 10 times larger than the Milky Way hot cores. So what we are observing here are super hot cores. These are the protostars in formation in the center of this starburst galaxy. And the total luminosity of this proto-star phase is estimated to be like 5% of the total luminosity. And then we put HNCO into place also, and then we do this diagram. And basically, in this plot here, what we observe is here is the mass of protostars plus the mass of already formed stars from the previous work compared to the mass of gas, and here is the abundance of HNCO. And then we see here an evolution, right? So we see here that when we have a lot of HNCO, a lot of fuel, HNCO is fuel, then the mass of stars forming is slow compared to the total amount of gas, but then we have this quick jump. As soon as the stars start forming, then the number, of course, as soon as they start forming, the number of stars and protostars increase quickly, and then the abundance of HNCO rapidly decreases. So what we are observing here is we are actually being able to see the early stages of the new generation of superstar clusters in NGC 253, one of the prototypical star-forming galaxies. So that's it about the examples. That's it. Like, well, I was just handpicking different molecules just to show you how to work. But I've been talking mostly about abundances, right? But in order to do a precise work, we can do multi-transition analysis, right? And oops, I did? No. And I just wanted to introduce you to this Alchemy, which is a large program at ALMA, which was just finished. Most of the data are delivered. And this is stands for ALMA Comprehensive High Resolution Extragalactic Molecular Inventory. So it's not only me, it's a lot of alchemists here, including this proposal, which I'm leading together with Nanasi Arada in Taiwan and Jeff Mangum in NREO in the US. And on the way, we just accreted. I mean, the data is so rich that we've been accreting something like 10 postdocs and students which were interested. There's a lot of data. If anybody wants to pick some, just let me know. A lot of stuff to do. And this last project was aimed to do a spectral line imaging survey of the central molecular zone of NGC 253. Again, NGC 253, the top prototypical starburst, is one of the brightest molecular emitters in the sky. And this to be done at an unprecedented resolution and sensitivity. So basically what we did is to image just these central regions, which is equivalent to the central molecular region within our galaxy. And at a resolution of, we expected something like 15 parsecs, but then what ALMA delivered was something like in the order of 30 parsecs, so at least enough to identify the individual molecular clouds. And the frequency coverage here was basically covering almost all the low frequency bands of ALMA from 84 gigahertz to 368 gigahertz. For those used to wavelength, this is from 3 millimeters all the way to 0.8 millimeters. Okay, and at very high sensitivity, and actually the band 5 intermediate band was a cycle 6, just a recent extension that was unfortunately not finished. And these were the main science drivers. This is all the blah, blah, blah that you do in the proposal to get the time, saying that we wanted to do an uniform, very uniform beam match extragalactic molecular inventory, to be able to image the physical conditions at the galaxy, to determine the stellar processing through the study of isotopic ratios, measured with isotopologues, molecular isotopologues, and then to make, you saw before the comparison between NGC 253 and the center of the Milky Way. Now we have a kind of similar resolution to low resolution observations at the center of the galaxy. And then also I'm also interested on the origin of life, so how we form the more and more complex species, and now we are able to study this also in extragalactic environments. This has led to a lot of currently ongoing projects. I'm currently going through the central molecular zone chemical zoo, and what I mean by chemical zoo is something like this, right? This is before I was talking to you about this molecule, these other molecules, and this is what you get when you go really wide. With this, just to say that typically we are used to see this in local star-forming regions, right? Or in star-forming regions, low mass, high mass. You have this kind of complexity. But this is just the integrated spectrum of the whole central molecular zone of a galaxy at 3 megaparsecs, right? So this is absolutely unprecedented. And once again, this was only the 7-meter data alone. So this is convolved to this is homogeneously convolved to a resolution of 15 arcseconds. And I've been working on the modeling of this spectrum with Matkuba, and it looks something like this, right? Here is just a sneak peek to all the complexity that we observe. In orange is the model, and in blue the observations and all the species that we observe. And we have detected already something like 100 species on this low resolution data. So we are already almost double the number of species known in the extragalactic median. It's not confusion limited. I mean, it's not like hot cores when you have confusion between lines, but when you have a very large spectrum and you compress it a lot, it looks like confusion limit. So it's cool for the presentations, but it's not really that hard. And we have all these kind of molecules to study, but I will not get into the details of this. And this is also a preview of one spectra of at the most extreme star-forming clump in the galaxy. but where we only show the highest peaks. But we have way more complexity when we go at high resolution. I will be studying this starting as next week with a visitor in Santiago. Is this only for experts? And then I talk about molecules and doing super weird modeling. The idea is to try to make it, the same way that instruments like ALMA or instruments like SKA are trying to produce science-ready products so that everybody, even if you are not in the field, can use it. We are also engaged into having tools that allows you to model these kind of things without being an expert, right? And this is what we've been doing with MatCuba during, as I said, a decade now. This is a work initiated in Madrid. Now it's in the CAP, but it's been changing institute that Jesus Martin was moving around. But we've been involved on this for quite a long time now. And basically, same as SKA as it is now with ALMA. The data sets that we get are really enormous. Is it right, Anchor? Anchor has been uncompressing some data since yesterday, and it's still ongoing. So basically, we have a huge cube, and on each pixel of this cube, we have this spectra. For example, in this particular thing, it's like 20,000 channels covering 250 gigahertz of band, and we need tools to analyze this. And then, as I said, MatCuba has been developed for a decade now. It's been already used in a number of publications, but finally we had Impress a publication which explains how MatCuba works. And the idea here was for the software to be efficient and easy, both installation and use, right? And MatCuba is simply this. It's a program under ImageJ. ImageJ is kind of a Java platform which is used a lot in biomedical studies, but it's not much used in astronomy. And this is basically MatCuba that allows you to import data, open data, synchronize cube that I will show you now, and then analyze that. And it's an easy installation. You just need Java, and then you can basically plug it into an USB drive and start working with it in 5 minutes. And it allows you, for example, to open many cubes and synchronize them, right? So if you click here, you get the spectrum in all the cubes at this pixel. If you move pixel, then you see the spectrum moving, and then you can extract it, you can analyze it. And for example, in this example that I did for a presentation a year or so ago, I was basically open the whole survey. It was the data cubes are 300 times 300 pixels times 450 in velocity, but there were 116 cubes. And I was basically open all of them at the same time in my laptop, in this laptop actually. So it's 14 to the 9 pixels, and it can be handled with your laptop, right? And then it allows you to study the excitation. This is basically the very basic. If I understand it, it has to be basic, right? So it's very basic formalism of local thermodynamic equilibrium radiative transfer under a Gaussian, assuming a Gaussian distribution of the molecules, and the opacity is proportional to the column density. And this is you don't need to know how this works, but basically all the thing is done by MatCuba for you. And then it has the relevant spectroscopic databases as a standalone catalog, which is just right now it's 1.5 gigabytes. This is it's like what we download regularly. It's very light currently, 1 gigabyte. And then it allows you to do these kind of things by selecting a given molecule, and you can actually play with the sliders, play with the column density, velocity, temperature, width, and then you can fit molecules. It also has an auto-fitting algorithm to automatically fit the emission, so it allows you to easily and interactively handle this kind of spectra. I mean, a tutorial of this, as I said, could take 10-15 minutes, and you would be already playing with analyzing abundances actually, one of the persons who is involved in MatCuba, he's regularly giving seminars to high school students, and they analyze ALMA data and they play with it, and it's very easy to use. So as I said, I would finalize with some other examples. I've been mostly dealing with what I mostly do in extragalactic environments, but there's some others. I mean, this can be applied to almost anything. For example, a work that we published a few years ago about the dissecting the circumnuclear disk around the black hole at the center of the galaxy. So you know that at the center of the galaxy we have these beautiful stars which are being continuously monitored which was used to derive the mass of the central black hole. But around this central cluster, there's a lot of molecular complexity, right? We have a structure which is more or less like this. We have a circumnuclear disk of molecular material. We have a spiral, kind of a mini spiral of ionized gas. And then we have streamers here. We have the Sagittarius A East, which is a supernova remnant, another supernova remnant. We have these two big molecular clouds, which probably are feeding the circumnuclear disk. So it's really difficult. It's a difficult region, a very, very crowded region. But one of the nice things of chemistry is it can be used to dissect the different processes. For example, if we observe this, we are observing this thing here, the circumnuclear disk. If we observe this at high resolutions, these are SMA images from the millimeter array, and you basically observe almost everything there, right? The circumnuclear disk here, the same in these molecules, and actually the same if you observe in HCN, HCO+, yes, it's the same thing. But then if you observe the hydrogen recombination line, the story changes a lot, right? It's this color thing. Here is where you see this mini spiral of ionized gas. And then if you observe some other exotic molecules, then the thing changes a lot, right? Then you see, for example, HCO+, which, well, I put in this, which is showing some kind of circular structure, and probably this is related to the impact of the supernova remnant into the molecular material, which is being probably expanded here and then compressed in this region here. And then you have SIO, right? As I said, SIO is a tracer of shocks, right? So probably we are observing how this molecular gas, this molecular cloud is impacting the CMD. It's feeding the CMD and it's impacting in these regions, and mostly in these two regions. There's some subsequent studies which actually show that there was actually streams of gas that were coming down from these 20 kilometers a second GMC, which are probably entering the CMD through these 2 points. So as I said, you can do a multicolor image in which you are tracing the different processes, right? CN and HCO+ is basically observing almost all the gas, which is heavily impacted by the photodissociation from the central cluster and the black hole. And then we have the shocks mostly down here, and then we have this dense gas in this kind of round shape. And then if you want, you can also put the ionized material, and then you see how the molecular cloud probably is falling through these lanes and then ionizing as it goes into the galactic center. The same thing here and the same thing here. And then if you want to get creative, then you put the black hole and then you put some light, and then it's a beautiful image. Some other examples is the work that we've been carrying out with the Amiga group here with Lourdes. This was initially our first data in just one isolated galaxy, and we decided to go deep to see what we could observe. And this is what we got. I mean, we got all these molecules that they've been telling you about, HCN, HCO+, C2H, and H and C. And then when we put them in these kind of diagrams that I was showing you before, this is just the HCN, HCO+ ratio. So you see that this galaxy, 634, basically it's kind of in between. It's neither too high, neither too low. But then when we plot the C2H over HCO+, and the same thing over HCN or over H and C, so if you compare this emission with any of these molecules, then it's really, really high. I mean, significantly high. It's a factor of a few higher, at least more than a factor of 2 higher than these galaxies. And as I said, C2H is the byproduct of dissociating polycyclic, the PAHs, right? So then our conclusion was that probably this is because of the fact that since these galaxies are not heavily interacting, probably the gas is more diffuse, and it's also less shielded against UV radiation. So probably this is what we are observing here. It's a globally photodissociated gas all over the galaxy, meaning that it has a lower amount of dense gas. But of course, this was unresolved 30-meter data. Now we can go to ALMA and say, okay, what happens at high resolution? Let's see where the molecular gas is at high resolution. And this is not the Amiga sample. This is just to compare. This is a study that was done again with NGC253, in which now we have the resolution to study individual GMC. And in these plots, which is basically radius over line width, surface density over size line width, and radius over mass, we see how the GMCs in this star-forming galaxy are kind of above the general trend, observing this is the center of the Milky Way, this is the outer parts of the Milky Way, some nearby galaxies, and these clouds these heavily star-forming clouds are definitely higher density, and the free-fall times are much, much lower, which results in a very, very efficient star-forming region. The nice thing, and we were discussing this these days, is that Amiga is on the other side of the coin. I mean, here we are trying to understand why these galaxies are forming stars so efficiently. I mean, NGC 253 has the same mass of molecular gas as the center of our Milky Way, but the center of our Milky Way is not so efficient. And clearly something happened. The galaxies are more dense. Can we do a similar thing with the Amiga galaxies? And then, because this is a project from Lourdes was the PI of this approved project a few cycles ago, and then we sampled 20 galaxies. Only 5 minutes of integration with ALMA time. And then we had 4 out of 3 out of 21 source galaxies observed. I only showed here 3 because the 4th is like very, very, very kind of faint. But now the fun thing is that apart from other studies, other work that we've been kind of brainstorming these last 2 days, now we can do the same thing that we did on NGC 253, and then we can say, why the hell these galaxies are forming stars at such a low pace? Why they are so inefficient in forming stars? And then one would expect to have the isolated galaxies somewhere here, right? So this is what we are kind of pursuing now, apart from other stuff with these samples. And then we have the GRB environment, right? This is something that Antonio Duarte started here, which is pretty interesting. Instead of just studying the afterglow in the continuum in the continuum, he was trying to pursue something like what we observe here. This is the absorption towards a background quasar, and then we see deep. Basically, we have a quasar behind a foreground galaxy, and the quasar is magnified, and then basically we see the absorption of a face-on galaxy in front of a background quasar. And you see these deep features. The thing here, one interesting thing here in this absorption system is that the water is one of the deepest absorptions, right? Not CO. But the easy thing here is that in these quasars, basically we have a source in the background which is one or a few Janskis in intensity, and then you have these deep absorptions. When you go to GRBs, which are just a few millijanskis in intensity, the things get a bit more complicated, right? I mean, we basically saw no absorption here. And the question is why? Is it simply that ALMA is not so sensitive? And I was thinking about this after we published this result, and I was talking to Antonio yesterday. And the thing is that the problem is this: if we look at this formula, I mean, this is a very, very basic formula. This is a very if you have a background source and you have some cloud in front of this black cloud, in front of this background source, you will see emission if the excitation temperature of this cloud is higher than the continuum and the background together. And if it's smaller, you see absorption. Okay, it's very easy. And then if you have a very, very bright background source, like a 100 Kelvin source, then for no matter what your cloud in front of this intense source has, no matter what the excitation of this cloud, because in this large range of temperatures from a few Kelvin to, let's say, 50 Kelvin or so, it's more or less linear. So basically, the depth of this absorption is proportional to the opacity, and the opacity is proportional to the column density. So you see the depth, and you see, and it's a very efficient way of detecting molecular gas. But in the problems is that in the GRBs, we have a background source, which is very, very faint. It's just a few millijanskis. So we are not in the linear regime. Basically, the linear regime is only here. So probably in most cases, we are very close. So this value here is very close to this value here. And when both are very close, we get something like this. In the paper, we were saying that this non-detection, based on this linear approximation, was we were getting that probably the amount of CO there is like 10 to the 15, blah, blah, blah. But this could be 10 to the 20. It could be 10 to the 100. If these two values are too close, then you see nothing, right? So this is something that we need to understand and we need to overcome in the future. But the good thing is that, well, you do not detect the GRB, but you detect the host galaxy, right? The GRB is here. We see nothing in molecular emission, but you know where it exploded, right? And this is work which is ongoing, very, very interesting work. High redshift. It's like, okay, you have been all the time talking about low nearby galaxies. Do you have any hope for high redshift? Well, and this is clearly this is work under investigation. So this is So these are galaxies. These are observed with NOEMA. And this is a galaxy at redshift 4, and this is a galaxy at redshift 3. And then you see all this complexity. And actually, we got some surprises on this galaxy. But this is work currently in progress by a ESO fellow there in Chile, Chen Tao Yang. And same thing. We have. I was also collaborating. As you see, actually, this plot here is made with Matkuba, right? That I showed you before. And this is a galaxy. Actually, the line identification prevents you from seeing the lines, so I should have removed them. But basically, you have a huge complexity also at redshift almost 6. Okay. So. But the problem here is that in the ALMA bands, what we are observing is the rest frequencies of 800 gigahertz. So it's very, very, very high frequency on rest frame. But if we really want to go to the lower frequencies, this is what we will be able to do with SKA. There's many things to do, of course, with SKA, but within this field, the ALMA, what currently is the ALMA band 3 in local galaxies, will be redshifted to the SKA high frequency SKA MIDI whenever this is constructed at redshift 3. But we could go at redshift 6, 7, as I showed you before, and then it will go right at the SKA bands, right? And up to what redshift? One of the problems with redshift is that as you move in redshift, of course, the background temperature is increasing. So at redshift 3, you have the CMB temperature is 11. At redshift 7, it's 22. Actually, there's a mistake on the SKA Spanish white book. I was checking these things, and they were saying that it was 40, so probably they just miscalculated. The problem with this is that if the background is too hot, then, as I told you before, if the molecular clouds are not hot enough, you are never going to see emission, right? But there is still hope up to redshift 7. Of course, at high redshift, similar to local galaxies, the intrinsic line width is going to be large, so it's difficult to disentangle, but we have the tools. But we will definitely reach a similar complexity as what I showed you on NGC 253. The similar complexity probably will be reached at redshift 3 and 7, and then we will be able to trace a kind of a cosmic evolution of molecular material and molecular complexity. So all in all, I hope I have convinced you that you should put your ALMA hat, and not only the ALMA hat, but also the SKA hat, the NOEMA hat, and maybe use the molecules as your new toy or the new tool. So yeah, thank you for listening. I hope it was not too many molecules around.
Now it's time for questions. Yes.
When you talk about many molecules in a topic, then people get like.
Yeah.
Thank you for the very comprehensive talk. My question is about the alchemy. You say that you are doing beam matching observations, so you make sure that I guess at all frequencies you have the same beam size, which is very useful when you do line ratios. The question is, what about the filling factor? Do you think that the filling factor of the different molecules in this same beam are similar? So when you do ratios, you really do ratios of similar things? Or what certitude you have about that?
Definition, but you have to assume that they are similar, otherwise you cannot do ratios, right? So whenever you do ratios, so it's the same as when you calculate isotopology of ratios. I mean, if you are doing a ratio, it's because you work under the assumption that they are coming from the same region, but this is definitely not the case. But for global studies, even if they are not coming from the same region, what you want to see is how abundant some species is, right? So even if it's not coming from the same region, if you compare it with another cloud, probably in the other cloud is this given molecule is way more compact or way more extended, but what you are calculating is the total abundances. Then you really need to go to very, very high resolution, even though now at least we are resolving the individual clouds. So it's then you have to go to highly resolved observations if you really want to discern this thing. But this is what we do in the local universe, in our galaxy, right? Then you have the resolution to really precisely say from which region a given species is coming from.
Alchemy sample all these detections you have. Are you mapping them, or for how many you have enough signal to noise ratio to map? Is that integrated emission?
Yes, almost all of them. I mean, yeah. Yes. Yeah.
Yes.
So in alchemy, what are you doing with the continuum? Are you using it at all, or?
I think somebody, at least somebody on the group is gonna take care of that. But actually, one of the nice things is that in star-forming regions or in galaxies, you have the continuum from the dust, then you have the free emission, and then you have the synchrotron thing. And then typically this is differentiated by a few points, right? You have a point here, and then you feed whatever. Here we have all the spectral information from 1 millimeter, just almost you get all the information in the Rayleigh tails of the dust, and then you have you get the curvature at 3 millimeters, so you can do precise studies of these different contributions. Yes, it's definitely useful, and you can do it for each individual cloud, even at the very center on the AGN, or not the AGN, on the black hole. There's no AGN there. No polarization in these observations, but I was in a conference last week, and there was a colleague who had a polarization map of NGC 253 made with ALMA, and yeah, the result is interesting. But I've never been a polarization fan.
Any other question? Enrique?
Could you elaborate a little bit more at high redshift that you've mentioned? At redshift 5.7, which is the spectrum that you show, the universe is basically neutral except for small pockets around quasars or other ionizing sources. So the overall availability of UV photons is much lower. On the other hand, I guess in general the abundances are also lower because the metallicity would be still fairly low as redshift 6 or whatever, 7. So could you say a little bit more about that?
This is definitely work in progress, eh? And actually I didn't ask for permission to show these things here. But you see that at redshift 3, 4, or even almost 6, I mean, you have a lot of stuff. I mean, you have a lot of CO, definitely a lot of water. This is basically the bands observed by Herschel, right? But these are redshifted to the ALMA bands at this redshift. But we definitely have to check how these abundances are compared to the local universe. To see whether it's really neutral dominated or these molecules are already abundant at this redshift, right? I mean, the ALMA observation has shown that the dust is already produced, and really there's a lot of dust already very, very early in the universe, way earlier than we thought, and the same with the molecular gas. And then we also have to analyze. I mean, if we have dust and we have molecular gas, the chemistry scales are going to be relatively shorter, right? So that's why we observe all this complexity. But at these high frequencies, we have the hydrides, we have these basic molecules. If you want to really get to the more complex species, you have to go lower in frequency, and or to get to this kind of organic, even if it's only methanol or ethanol, right? You have to go to lower frequencies, and that we cannot access nowadays. We will have to observe this high redshift with SKA. When this band 3 is really moved to the SKA band.
Well, thank you, Sergio. It's very, very interesting talk. Just a curiosity, for alchemy, for NGC 253, do you have I mean, I'm sure you have, but you have the possibility to check the SEO with the rims or the position of dust, because I was missing dust in your talk. You say
I'm not a dust person, but
are you related to the shattering?
That I don't know. So what did you miss about the dust? Just
Theory for the production of SEO from the dust grains, and this is still, I mean, it's a scenario, but the details are unknown. So are you? I mean, what alchemy is going to contribute on that, or because?
I mean, as I said, I think we are mostly using. Let me check. no, where is it? It's up here. As I said, we want to use, I mean, we as Galactic use mostly we use mostly the results that we understand in detail in the galaxy, right? So if you really want to compare the dust emission with the ACIO emission, you really have to go to the galactic center to really pinpoint where this is appearing, right? At this resolution, everything is going to be merged, right? And actually, you have here this is dust. This is 350 gigahertz dust continuum emission, right? And then yes. I haven't shown the comparison, but the SIO emission looks very similar, mostly on this region here and here, right? But still, this is at 2 parsecs scale, right? So it's you don't have the resolution to really match. But I'm not sure whether this comparison between DAS and SIO has been done, but that's definitely something to be done. Yes.
You mentioned as is in relation to this isolated galaxies. Investigation. So, do you have can you elaborate, or can you just show us something? What is the real cause, or what your idea of the situation? Why is not the star formation is not?
In cases we know that the star formation can be triggered by interaction, right? I mean, or this star burst will be triggered by some event that will cause the gas to inflow into the center of the galaxy, right? If you don't have these interactions, probably this transfer, although it will be done by nature, right, with time, but it will not be so efficiently triggered, right? And then maybe that's the reason why we think that the distribution of the molecular gas is not so centrally peaked, and I think that was part of some of the work that Ute did in the past about the central concentration of the gas. I think, if I'm not wrong, and. So then you will have a more distributed gas, which will naturally collapse and form stars, but not in a bursting mode. And then in order to understand whether this is the case, now we have the resolution to really pinpoint individual clouds. And then we have the same way that it's been done on NGC243, and say, okay, why is it so efficient? And then you see that the clouds are definitely denser. I hope that we see the same on the other side, or at least we will see what we see. This is super preliminary, so it might be very interesting the result, because I think Amiga galaxies is the other side of the coin compared to starburst galaxies. So I think it's very promising.
I have a question myself with respect to AGN. You've said that when you see at high resolution, you don't see the molecules in the right in the center, but a little bit farther. Isn't it logical? I mean, the power source of the AGN itself shouldn't be destroying the molecules if they are too close by?
It's similar to the photodissociation region around stars. Of course, the stars destroy the molecules, but there's a region, this photodissociation region, this kind of thin layer in which you still have molecules, but they are highly UV radiated. The same thing will happen in the sphere, around the sphere of influence of the AGN. Of course, really, really close to the AGN, all the gas is going to be ionized, and well, we have an image right now. We have an image now of all this plasma gas, right? You don't expect to see these molecules this close, but you will have the same thing, kind of a sphere of a thin layer of heavily radiated gas, where you can have a similar chemistry to what you have on photodissociation regions. But the thing is that this area is very, very, very small. So that's why you don't, even though we expected to have this super enhancement of HCN, that was based on some side results from some chemical models. So it was basically people trying to understand this enhancement. They just grasped the models that they had at the time, and they said, okay, under these conditions we formed that. But even the person who did the models at the conference, I remember that he said, well, mate, you made a very bad use of these models. But now we understand it. And now we think we understand it by this enhancement through outflows. So it's related to the AGN, but indirectly.
Do you have the one-to-one connection in others, I mean, kinematics or whatever that you see with other traces in which you see the outflow and you see the connection with the outflow?
It has not been done. And but that, yeah, that's I guess that's in progress. Yes, that has to be done. if that's the case, we should see a connection with the outflow presence or the velocity of the outflow itself.
Any other question? Ivan?
Yeah, regarding the case of the high redshift molecules, because of the problem of the high temperature of the environment at those high redshift, perhaps, I mean, have you considered the case of trying to detect those molecules at in absorption against, for example, radio loud AGNs that emit a lot, and then it could be easy as the example that you showed? Yeah.
On PKS 1820, whatever, I never remember. That's actually one of the extragalactic sources in which most molecules have been detected, because detecting it in absorption is really, really efficient. But the problem is that the molecular absorbers are really, really scarce. There's only a handful of them. Actually, some people have been using the ALMA archive of the calibrators to try to look for absorption in the line of sight of these quasars. But some have been identified, but they end up being galactic absorbers. So it's really, really difficult to find these molecular absorbers.
Any other question? So if not, we acknowledge again Sergio for such a nice talk.